Здравствуйте, Максим. Меня слышно? Такой вопрос к вам.
Здравствуйте, да, вас хорошо слышно.
Сейчас, подождите. Скажите что-нибудь еще раз, Максим.
Да, вас слышно.
Угу. Так, тогда нам еще надо прибавить. Здесь. Так, остается Телебжон и Ильнас. Да, по сути. Ой, так, раз, два, три, четыре, пять, шесть, семь. Угу. Так. Затем мне нужно
Нет, я вдохновился. Вчера мероприятие ходил, я смотрю на их компьютер. Нет, я взял их элементы с сайта, с обложек, составил сам.
Это...
Я фотографию делал.
Картинки.
Ребята, те, которые онлайн, меня слышно, да? Все хорошо ведь? Еще раз уточню. Ага. У вас тоже плюс-минус слышно. И видно мой экран вам, то, что я предоставляю. Ну, вот видно то, что листы показываю?
Да, видно.
Ой, там возможно, Максиму нужно прибавить микрофон, а то по сравнению с другими потише. Ладно. Не суть. Сегодня первая попытка. Вроде бы получилось все настроить. Давайте начнем с прошлой лекции. Так. So, welcome in today's Advanced Array Signal Processing lecture. Before, in the previous week, we started with recursive least squares algorithm. So, the main thing here that rate of convergence is faster than usual least mean squares algorithm, but in this case, of course, we will increase the computational complexity. And here, let me maybe one more time give this information. So we receive U for different time snapshots, let's say, in this case from for I, which goes from 1 up to n. And for each this signal, we compute this y of I, and we compare it with d of I, and then we find this estimation error for the time with index I here. And in this case, for errorless algorithm, we represent our cost function in this way, using weighting factor or forgetting factor, which is between two values. So from the left side, it is 0, and from the right side, it is 1. So it is only greater than 0, and it is less or equal to 1. In this case, we can use for these weighting factors, let's say exponential scale. In this case, you can see we have some lambda in the power of n minus I for this weighting factor beta for indices n and I, where n it is the length of our data window, we can say observed data window, and I it is these elements inside of this window. And then you can see we will have this type of cost function where the in this case the last value E of n will have weighting factor equal to 1, and the, let's say, the first value which we have inside of this window will have the weighting factor lambda in the power of n minus 1. And here you can see in the table the measure of memory for different lambdas. And of course, if our lambda is equal to 1, we will have, and with assumption that n goes to infinity, we'll have infinity rectangular window, which means infinite memory, or is equivalent to least squares algorithm. And then we introduce a regularization term, and we end with this normal equation. And the main question here, when we calculate the partial derivative, what we'll have after this normal equation for this R of n we've had and P of n we've had. So first one, it is covariance matrix for the input signal. And the second one, it is covariance vector between input signal and desired response. So it is lecture number 15, I think. Yes. Lecture 15, 2022, October 25th. So next, here we have two assumptions to introduce our estimate of a covariance matrix for index n. We assume first one, if we try to find the expected value of our input signal, so U of I. Okay, let's use, I think, vector notation here. We will have 0, so it is 0 mean vector. And if we also compute the expected value of our desired response, it will be also 0. So 0 mean input signal. А? Поближе? Здесь она нормальная просто, поэтому давайте я попробую чуть-чуть. Это нет. И здесь уже снова плохо. То есть где-то вот тут, по сути. Лучше не стало, да? Но я могу попробовать перевернуть. Давайте, может, раз это уже такой экспериментальный у нас. Здесь можно каким-то образом это перевернуть. И здесь изображение перевернуть вроде бы. Но это уже хороший вопрос этой техники. Да, садитесь поближе, там все равно, скорее всего, никого не будет. View, full screen. Так, вот это точное освещение. Или же... Нет, так тоже не получится у нас. Я более чем уверен, что здесь можно каким-то образом это перевернуть. Возможно... ну, да. Это будет то же самое. Либо же мне попробовать еще чуть ближе сделать. Сейчас давайте попробуем тогда. Немного в ущерб самой картинки. То есть я буду передвигать сам листки. Но сделаем чуть поближе листок. И уже тут теперь. Как-то вот так, наверное. Получше? Хорошо. So, we assume 0 mean input vector and 0 mean desired response. Then, for covariance matrix, we will have next equation. Matrix R we've had for n is equal, and if we look to the previous equation, which connections here we will have? So we have the sum for here inside lambda with power n minus I, which is multiplied with u of I and u of I Hermitian, where I goes from 1 up to n. And we need to add this regularization term here. So it will be plus delta multiplied with lambda in the power of n times identity matrix of size m. I will put this equation into the box and also add background color, yellow background color. So we can call this equation as time averaged diagonally loaded temporal correlation matrix. So it is time averaged diagonally loaded temporal correlation matrix. Temporal correlation matrix. And then what does it mean with regularization term here? So it will be something like initialization point. So we'll talk about it later, but also I will add some notes here. So this one is our regularization term. Regularization term. And it makes, so let's write, makes our matrix R and we've had non-singular at all steps of the computation. At all steps of the computation. And of course, starting at n equal to 0. Starting at n equal to 0. And let's assume this first or initialization step, let's say, not the first step, but initialization step. So n equal to 0. In this case, this temporal correlation matrix R for n equal to 0 we've had will be equal to this regularization term delta times I identity matrix of size m. And for each step, you will forget some parts of this data, because if we go back, usually our lambda is less than 1, and you can see here we have lambda in the power of n, and if n goes to infinity, we will this part will go to 0 in this case. So n goes to infinity, then we gradually forget this initialization. Then let's introduce based on our input signal and desired response time averaged cross correlation vector. So it is this vector P we've had. The second one, and that may be for the future. So we need somehow to do it in this way. And let's continue. Next one, time averaged cross correlation vector. Time averaged cross correlation vector. I will also indicate it with blue underline here. So this cross correlation vector is vector P we've had for index n is equal to the sum as before. Here we have this exponential value lambda in the power of n minus I. And as before, for this cross correlation vector, we need to multiply input signal u of I with complex conjugate of the desired response. And of course, I goes from 1 for this sum up to n. I will also put this equation into the box. And then we will slightly modify our temporal correlation matrix. The next step, we want to isolate the term for I equal to n. Isolate the term for I equal to n. In this case, we can rewrite our matrix R with head in the following way. So R with head for index n is equal. First, here we have lambda multiplied with. Inside of this bracket, we have the sum for I from 1, but in this case, it will go to n minus 1. So we want to isolate this n term. Then lambda will have power n minus I minus 1. And the rest thing will be the same. So U of I Hermitian. and of course plus regularization term plus delta times lambda n minus 1 identity matrix of size m so all this thing inside of this bracket is temporal correlation matrix, but for index n minus 1. But of course, we lose this U of I for index n, and we need to add it here at the end as U of n times U of n Hermitian, like this one. Or simply we can show it in the following way. So our time averaged this diagonally loaded temporal correlation matrix is equal to the previous value of this matrix plus, of course with lambda here, plus the new value of our input signal. So U of n times U of n Hermitian. And let's put this resulting equation into the box and also highlight it with yellow color. In the same way, we can represent time averaged cross correlation vector. So do the same thing for P with head of n. In this case, we will have cross correlation vector is equal to this lambda times the previous value of this cross correlation vector plus U of n times d of n complex conjugate. And also I will put this one into the box, but I will leave it with white background color. And then I need to introduce the matrix inverse lemma, because we will use it to derive equations for recursive part, this recursive least squares algorithm. So I think I will continue here. Matrix, or maybe, okay, let's use another page here. Matrix inversion lemma. So let's assume that we have two matrices A and B. So we have matrix A, matrix B, both positive definite. So it is positive definite. And they have the sizes m times m. So A and B, they are complex matrix of size m times m. And let's say that we can, or not, let's say that we have the connection between these A and B in the following way. So the matrix A is equal to the inverse of the matrix B plus multiplication of the matrices C, inverse of matrix D, and the same matrix D with Hermitian. Often for these matrices C and D, so often or let's maybe, yeah, start that if we compute A Hermitian, we'll have matrix A. If we compute B Hermitian, we'll have matrix B. And if we compute D Hermitian, we'll have D. Then we need to, let's first introduce the vector C. So, oh, of course not the vector, matrix C. Matrix C, it is complex matrix of size m times n. And here, the matrix D, it is positive definite and of size n times n. N times n. So we have here three matrices. So two of them of size m times m, one of them n times m, and the last one of size m times n. And here, often we'll have that n is less than m, like this one. And what we have inside of this matrix inversion lemma. So if we have the matrix A, which is equal to this expression of the matrices, for the inversion of A, we can write down the following equation. So matrix A inverse is equal to the matrix B plus minus matrix B times matrix C. Then we have here bracket, and inside of this one we have D plus C Hermitian times B times C, all this part with inverse sign, and the last two matrices, it is C Hermitian times B. And let's put this equation into the box. And I think it will be good if we put into the box the definition of matrix A with inverse of B plus C and etc. So this one also into the box. So it looks like some black math, of course. If you want, you can prove it. So we can prove all this thing. Prove this via inverse of A times matrix A, and this one will be equal to identity matrix. So if we take this part and multiply it with this part, you will have identity matrix. Here, a lot of mathematical stuff, but I can say you that you will have, as a result, identity matrix. So all this introduction of matrix inversion only for now. We identify the matrices with matrix A, B, C, D for our recursive least squares algorithm. So identification for RLS. Based on the matrix A is equivalent to temporal correlation matrix for index n. Then the inverse of the matrix B, so B inverse, to lambda times previous value of temporal correlation matrix. So here we have R with head n minus 1. Then matrix C, for our case, it is input signal with index n. And the last one, matrix D, So it is equal to 1. And we will use all these matrices to calculate the inverse of our temporal correlation matrix. So R, we've had inverse for index n. If we look to the previous question, yeah, that it is equal to inverse of lambda times inverse for the previous step of this matrix. So R, we've had inverse n minus 1 here. And you can see, so inverse of matrix A is equal to the inverse matrix B, but here we have for inverse of B this one, so we need to take the inverse part of this one, then minus B times C, so minus B, it is inverse of lambda, times the R we've had inverse for index n multiplied with C, it is our input signal U of n. Then we have D here. It is just 1 plus C Hermitian. So it is Hermitian of our input signal. U of n Hermitian times B. So it is original B. This one, it is inverse of R we've had for n minus 1 times C. It is U of n. All this part with inverse sign. Right. Thank you. Here, inverse of R. And last two parts, it is C Hermitian and B. So here, C Hermitian is U Hermitian of n, and B, it is this lambda minus 1 times R with head inverse n minus 1. So all this part, I will indicate with brown color. So from it is B times C and this inverse thing here. We will call it as gain vector. So let, for simplicity, use matrix P, which is equal to inverse of matrix R for index n. So it is inverse of the estimated temporal correlation matrix. Temporal correlation matrix. Then our gain vector k of n will be equal to, so k of n equal, so I will use the same brown color here. So this k of n are the same things. So here we have a fraction. In the numerator, we have inverse of lambda times this new matrix P. So and times U of n. And in the denominator, we will have all this part. So it is times inverse of lambda times P, matrix P of n minus 1, and times I will put this equation into a box, and then this one into the box. Vector. And also I will add because we will use it later. Then we can for time index or iteration n. It will be this matrix P of lambda times this matrix for the previous iteration. Then minus okay, minus another one here at the end. So let me show you first here. So we move it to first. K of n. Then inverse of input signal, U of n Hermitian. let's keep this color thing here, because without this P of n, P of n minus 1, P of n minus 1, as before with blue underline here. Riccati equation. Is this? What тут? So it is Riccati TI, Riccati equation for the RLS algorithm. Inside of this RLS algorithm, we'll have a lot of mathematical stuff. We need to show one more time one part for this gain vector. To adapt our weight vector somehow. But of course, we'll start with gain vector. So let's use reference for here we can multiply both sides with the denominator. So this one will go to the left side plus u of n Hermitian times lambda the inverse times p of n minus 1 times u of n, and of n minus 1 and u of n. As before. What we'll have here, you can see we will have 1k here and 1k for this long thing. So we can, in this case, leave so we leave this one from the left side, k of n times 1, and we move to the right side all this part our input vector U of n, this one and this one. In this case, we will have, so first I will write p of n minus 1, and then our negative part, so this one, minus so lambda inverse times u of n Hermitian times p of n minus 1 and let's see. So the same k of this equation to this equation, Riccati equation. We have inverse of lambda sorry. Of course, here we need to add this k of n is p of n minus 1. So all this part is the inverse iteration n. All this part. And as a result, so let me move this paper a little. And show that our gain vector k of n is equal to the times with our input signal for iteration n. And of course, let's use it. Let's show it in detail that k of n is equal to the here I will use so this equation may be used as definition and then I started it lightens the input data by using of inverse of this matrix, so of the correlation matrix. And here you can see This whitening, if we try to translate it in Russian, will be обелить, но в том плане то, что и мы обеляем наш сигнал. So maybe used as a definition of the gain vector. Yes, it is a little bit hard to understand from the first view. I will give you, let's say, short. In pseudocode, something like this one. Here, for this RLS algorithm, develop. For updating, estimate of our weight vector omega n iteration n. From previous adaptive filters, we know that our R with vector P. So here we have inverse of matrix R then instead of R of n, or let's say inverse so here we have matrix P of n times change our vector P of n using matrix P of n instead of cross-collateral previous iteration plus U of n So this thing is equal to then we can open and multiply these two parts with P of n. Times vector P with head n minus 1 of n times d of n complex conjugate. Next step, we will rewrite equation. Then we will have n. So omega n is equal let me show you. Ah. We'll use inverse of lambda and inverse of lambda. So if we put here Riccati equation, we have just the matrix P for iteration times U of n Hermitian times P is multiplied with cross correlation vector P with head of P of n times U of n times d of n complex conjugate. And from definition of this matrices P, this one, it is estimated temporal correlation matrix for iteration n minus 1. And this one also. Next, if we introduce but for iteration n minus 1, what we'll have? It is omega n minus 1 n minus 1 instead of n. So it is r with head, and here index n minus 1 here. And you can already see that in previous equation we have here inverse of also for index n minus 1. So here. Let me. We can rewrite an equation for omega. Then minus our gain vector times our input signal plus d of n complex conjugate. And let's use brown color for what we will have here. So it is P of n it is our gain vector. So K of n, P of n, P of n. So this part use brown color. Based on all these equations, we can write down the resulting equal to omega n minus 1 this plus our gain vector K of n so first let's write down things with positive and complex conjugate and then with negative sign. Omega n minus 1. Ребята, мы вернулись. Надеюсь, вы меня слышите. А сейчас,
Да, все отлично.
я вам еще и предоставлю демонстрацию экрана. Видите, слышите?
Экран пока не видно.
Хорошо, ждем. Видите? Давайте посмотрим. Так. Так. Видно экран, ребят?
Да, видно.
О, супер. So, давайте продолжим. Скорее всего, вот как раз априорно. Там они написали в 10 минут. Если вы сразу же написали, как отключилось, или чуть-чуть опоздали?
Сразу примерно.
Мы успели написать только половину VN, короче, и потом выключился.
Ага. Мы будем называть вот это выражение априорной ошибкой. Почему? Потому что если мы посмотрим саму формулу, у нас есть так скажем, нужный нам сигнал для времени n. При этом у нас есть принятый сигнал как раз в этот момент n, но сами значения нашего фильтра, они еще не обновились. То есть у нас используется n-1. И поэтому за счет того, что это значение прошлого фильтра, так скажем, еще не адаптированного фильтра, мы будем считать это как априорной информацией, потому что она базируется на прошлых значениях. Но у нас еще будет апостериорная информация, то есть на ошибка текущая. Давайте запишем это здесь, на словах, чтобы это не забылось. Since we have this, yes, we can write down in the following way. So omega Hermitian n-1 times with u of n, since this multiplication represents an estimate of the desired response based on the old weight vector. Based on the old weight vector. Возможно, вы слышали, как применяют вот само слово априорная информация. То есть она якобы нам уже заранее известна. И вот тут как раз-таки, почему она известна? Потому что она уже базируется на не обновленном фильтре. А вот актуальная ошибка, апостериорная, она уже будет высчитываться, используя омега-n, то есть уже обновленный вектор. Но для данного алгоритма это не обязательно. То есть, надеюсь, вы успели записать. Я сейчас добавлю здесь одно слово и вернусь. Если мы хотим именно посчитать ошибку текущую, E of n, we will call it as a posteriori posteriori estimation error. Yes, we can use this a posteriori estimation error to compute our cost function in this case. If you go to the beginning of our lectures, I will show it here. We represent our cost function using weighting factor times a posteriori estimation error. And here you can see, of course, it is equal to d of I minus omega of n and u of I. So now maybe let's make this break, and then I will give you the summary of the RLS algorithm, which will show you how we need to calculate all these parts. So it is really, let's say, short notation of this algorithm. Да, сам алгоритм, как вы видите, ну, пока у нас идет перерыв, видите, насколько он сложнее, например, относительно того же least squares. Когда least squares мы просто приняли сигнал, посчитали ошибку, потом что мы делаем? Для обновления мы приняли сигнал, посчитали ошибку и обновляем просто как наш принятый сигнал, умноженный на комплексно сопряженную ошибки. И все. А тут нам приходится дополнительные вещи рассчитывать. Получается, обратную матрицу нашей корреляционной матрицы. При этом, как вы видите, она именно time average, потому что мы принимаем сигнал, обновляем этот этап, принимаем, обновляем, принимаем, обновляем и так далее. Короче, 4
Aasp я был уже в среднее время, это 8 часов. А расстояние там будет километр. Просто большой будет. Потом получается, мало по трассе и фотку на 3. Примерно стоимость.
Ну, вот у меня всегда такое, автобус выезжает из города, вот ровно 3 часа.
Мне кажется, на 2 дня. Дальше я вижу. Да. Эй,
Прием, Китай.
я вчера ездил,
Че? Провизор?
Нет.
Но игры записали мне на первое игры. Сказали, вот за.
Москвы.
Нет. Что дадут документы визоваться. Ну, не визоваться, а правда. Первые игры. А игры вот сегодня вот, ну, дал им документы.
Обязательно получишь документ, потом поедешь в Москву, потом подашь.
Ну, нет, там типа подадут на визу 1 ноября мне. А игры сегодня подали на визу. Я думал, я тоже думал, что сегодня у меня. А потом мне сказали, что вот, 1 ноября. Ну, отлично.
Ну, там одна неделя? Одна неделя, по сути? Ну, неделю подождать.
Че, что ли? Уважает себя. Нет, они просто любят глазами.
Получает. Нормально.
Продолжим. Дальше чуть полегче будет. Там начнется, получается, новый, ну, так скажем, не параграф, новая тема, как раз определение параметров сигнала с высокой точностью. Там мы начнем просто, ну, пока бежать по основным вводным данным. То есть там, что за сигнал мы представляем, каким образом, что подразумевается под углами там азимута и так далее, и так далее, и так далее. То есть это будет такое же, чисто именно на писанину, не на сильное давление по пониманию, так скажем. Ну да, RLS-алгоритм, он достаточно такой массивный для понимания, там сразу туда вкатиться очень трудно. Но сейчас я вам покажу основные пункты, и уже будет плюс-минус понятно, хотя бы видно со стороны. Когда вот глядишь вглубь во все эти формулы, там очень страшно, так скажем, изначально. Ребята, вы здесь? Меня слышно? Видно?
Да, все хорошо,
Да.
мы с вами.
Да,
Всё.
все нормально.
Супер. Тогда продолжим у нас обобщение нашего алгоритма. Давайте я буквально перед началом чуть-чуть поправлю камеру. Чтобы можно было писать просто прямо. Как-то так. Summary of the RLS algorithm. Summary of the RLS algorithm. I will use double underlines here. О, это он сам решил подкорректировать. Вот так чуть по чуть вроде бы. First, we start with initialization. And after all this algorithm, I will put it in the one big box. So keep it in mind. So first, initialization. Of course, first we need to have some initial point for our weight vector. It is omega 0, and we will start from 0 point. So it is 0 vector. Then we need to introduce this inverse of the estimated temporal correlation matrix. So it is our vector P. E with 0. It is, if we go through the definition of R. Let me show you. Yes, but this here in the beginning of the lecture, I give you short note that R with head for n equal to 0 is equal to delta identity matrix of size m. So we need to calculate the inverse of this part. So it is inverse of this delta. Here we have inverse of the delta. And of course, if we calculate the inverse of the identity matrix, we'll have the same identity matrix. And let's add here that it goes from that our R0 is equal to delta of identity matrix of size m. Then we can ask, so what does mean this delta? So it is some just scalar thing, and we will have two different cases for this delta. Delta is equal, and here two cases. First one, it will be small positive constant. So small positive constant for high SNRs. For high SNRs. And vice versa. It will be large positive constant for low SNRs. Large positive constant for low SNR. And then we can go to the main part of our algorithm or of our loop. So for n equal to 1, 2, etc., we need to compute the next things. So we need to compute so first, it is new vector here P. We will use it to simplify how we write our following equations. So vector P of n is equal to this matrix P n minus 1 times received signal for index n, u of n. And as before, we can use blue color.
Что это за вектор?
P. То есть, ну вот число P же есть у нас. Мы просто используем это в виде буквы P. And we'll call it just as intermediate quantity. Это получается Сейчас, пока буду писать, вспомню. Intermediate quantity. Это как временный расчет, что ли, так скажем. То есть это просто для упрощения следующих формул. То есть, чтобы нам не писать каждый раз P of n minus 1, U of n, мы будем использовать просто P of n. Достаточно короткое обозначение. So, first with intermediate quantity, then we need to calculate gain vector. So, gain vector, which is equal to this, or denoted as k of n, and equal to the fraction in the numerator. We have this vector p of n, or p matrix p of n times q of n, and here below we have lambda plus u of n Hermitian times the same p of n. So this is our gain vector. And then you can see that, okay, maybe I will continue and then I will add one more thing here for gain vector. Then we need to calculate a priori estimation error. A priori estimation error. So it is with calligraphic E of n which is equal to d complex conjugate of n minus omega Hermitian, but for the previous step, n minus 1 times u of n. And then we need to update omega n. So let's write down gain vector, a priori estimation error, update omega n. Here we have omega n is equal to omega n minus 1 plus the gain vector times this a priori estimation error complex conjugate. And the same k of n. And last step, we need to update p of n using Riccati equation. So Riccati equation we will have p of n is equal to inverse of lambda times P of n minus 1 minus inverse of lambda times gain vector K of n times input signal with Hermitian. So U of n Hermitian times P of n minus 1. So here the same gain vector. This goes P of n, P of n, and P of n. And if we go back to intermediate quantity, let's see. For intermediate quantity, we have P of n minus 1 times U of n. And here we have U of n Hermitian times P of n minus 1. So if you remember that with P of n, it is just the inverse of this estimated temporal correlation matrix. So if we take the Hermitian of this matrix, we will have the same matrix. So correlation matrix, Hermitian, the same correlation matrix. In this case, it works in the same way with this P of n minus 1. So if we calculate the Hermitian of P of n minus 1, it will be the same matrix. So we can add here that this one is equal to the vector P of n, but with Hermitian sign. And then we can rewrite this Riccati equation in the following way. So let's move out lambda inverse. And here inside we have the previous value of this matrix P minus K of n times our intermediate quantity with Hermitian. So P Hermitian of n. This one with brown, with one, and this one with blue. And let's look one more time to gain vector and add short notation here. Because if you remember, when we try to calculate the inverse of some matrix, we can have some problems. Because sometimes we cannot invert our matrix. In this case, we need to use pseudo inverse, etc., etc., etc. But if we look to our equation, so we use some intermediate quantity, P of n, which is based on this multiplication. If we look to the first step, it is just identity matrix times U of n. And we can say that instead of using this inverse of our correlation matrix, we will use this updating thing first based on identity matrix and then based on this part. So we, let's say, do not calculate in the direct way, but we use some tricks to get this inverse of a correlation matrix. So here, for gain vector, we can add that scalar division replaces the inverse of the correlation matrix. The inverse of the correlation matrix. And that's all for our errorless algorithm. So I will put all these, of course, all this algorithm into the box, and then we will go to high resolution parameter estimation. So when you look to this simplified algorithm, you can see that, yes, of course, it is more complicated if you compare it with, for example, least squares algorithm, but it is not so hard to calculate all these things. But the main question here can be how we choose the variable delta. So we just say that we use small positive for one SNRs and large positive for our SNRs. So on this thing, I don't have exact answer, but when I have also this lecture before, I tried to implement this algorithm in MATLAB, and maybe I will find some practical values for this delta, maybe, but I need to check. So let's go to the high resolution parameter estimation. А у вас после этого не будет пар. Не так? Отлично. Но все равно.
Да, не будет пары, мы домой пойдем.
Хорошо. Особо задерживаться не будем сегодня.
Ильдар Айдарович, я вопрос в чате написал. Можете ответить, пожалуйста?
Давайте я посмотрю. Let me check. Так. Вопрос. Я не знаю, было ли видно вам. Что есть это P of n, если именно думать насчет сигналов? В данном случае это будет как раз псевдообратная матрица от нашей корреляционной матрицы. Но мы ее будем считать не напрямую, а мы сначала ее задаем вот как identity matrix, умноженный с каким-то переменным, который будет соответствовать либо high SNR, либо low SNR. Если вот в дальнейшем смотреть, если так просто подумать в голове, мы ставим здесь n равно единичке, p равно нулю, u равно единичке. Если p равно нулю, то это просто identity matrix. То есть здесь какой-то первоначально это будет просто p of n equal to u of n, потому что мы чисто берем identity matrix, но при этом с каким-то изменением, потому что у нас есть это дельта впереди. Затем мы высчитываем гейн-вектор. Ну, там здесь интересно нам именно последний этап. Что мы будем здесь иметь? Здесь у нас, опять-таки, ставим 0. Это identity matrix. Здесь, ну, лямбда, понятно, это какое-то значение от наших вот этих потерь. Гейн-вектор и умноженный, опять-таки, если смотреть, это будет наш входной сигнал. И то есть мы будем обновлять вот это, как бы правильно это выразить, нашу якобы псевдокорреляционную матрицу вот таким образом. То есть это, по сути, обратное от нашей корреляционной матрицы, но при этом она посчитана достаточно хитрым способом, чтобы не сильно нагружать и высчитывать это все. Вот. Но если вот вы посмотрите сюда, то как бы у нас все равно есть, ну ладно, тут это получается не сколько корреляционная матрица, у нас будет это просто одно значение, потому что у нас вектор строка на вектор столбец, да. Тут немного другое, конечно. Но вот как-то так. То есть это π относится к корреляционной матрице, но при этом оно посчитано не напрямую, чтобы еще больше не затруднять их подсчеты. И поэтому как бы у нас и появлялась вот эта странная формула здесь, потому что если вы посмотрите глубже, то есть у нас n равно нулю, то есть этой части у нас вообще нет. Здесь n равно нулю – это единичка, то есть мы стартуем вот с этого значения. Потом мы подставляем значение 1, здесь у нас будет лямбда, а здесь у нас будет первый входной сигнал, который будет в данном случае не забыт, потому что здесь у нас будет n равно, точнее, I будет равно самому последнему значению, как бы оно только-только пришло. Потом, когда мы перейдем на второй шаг, здесь снова изменится, это значение уже чуть-чуть забудется, а то, что пришло, снова сохранится. И вот так как бы оно идет. Но чуть похитрее, используя вот матрицу π. Там, в принципе, можно попробовать руками написать, шаг за шагом, и прям будет видно, что из чего выходит. Если вот идти, появится больше понимания, что внутри этого алгоритма. So section number 4, high resolution parameter estimation. High resolution parameter estimation. As before, 3 underlines and background red color for the name and for the section number. I think it will be better to start with some slides. So for this one, you will have another slide set. So slide set number 2. And for the beginning here, we have slides 1, 2, and 3. And this one is slide set number 2. Let me switch to the slides. So yes, first one, second one, third one. So we start with the objective. We are given with noisy measurements from a sensor array. In this case, it is not a, yes, I think it's not a MIMO, but a sensor array. So for example, linear array, in Russian it is антенная, нет, антенная фазовая решетка, нет, фар нужно вот.
Базовая антенная решетка.
Фазированная антенная решетка, да.
Фазированная.
То есть вот sensor array — это вот фазированная антенная решетка. И here we want to estimate a set of constant parameters upon which the received signal depends. And here you have 2 examples, but of course we can find more. First one, it is high resolution direction of arrival estimation. So from which side we receive our signal or our signals. And the high resolution spectral analysis of a time series. In this case, it is harmonic retrieval. It means when we have sine waves or complex sine waves as our sources. And we try to find the amplitude and the frequency of these harmonics. So let's go to the data model for direction of arrival estimation. Data model, DOA estimation. So let's say here we start this antenna, not array signal processing part. So before we have adaptive processing part, and here we have array. But of course, before also we use array, sensor array to get our signals, because we receive this U of n, which is vector, and these values are from sensor array. But here we focus on not on the data, but the direction of arrival of this data or of this signal. And of course, we start with some assumptions. So assumptions. Assumptions. First assumption, we have linear transmission medium. Linear transmission medium such that the radiation radiation impinging on an array impinging on an array of M passive sensors can be modeled as a superposition of D wavefronts generated by D point sources. And let me just indicate linear transmission medium. If we have now this linear transmission medium, we'll have some nonlinear processes, and in this case, we cannot model our system as superposition of these wavefronts. And the second assumption, one more point here, these signals possess the same nominal carrier frequency. The same nominal carrier frequency FC and distinct direction of variables, DOAS theta I, where I goes from 1 up to D. I goes from 1 to up to a number of sources. So here we indicate that signals have distinct direction of variables, and they, let's say, have the same nominal carrier frequency. FC, let's add here theta I. And the last assumption, what we need to have here. So we assume that our signals are narrowband. So we have D impinging wavefronts. Impinging wavefronts. And they are narrowband. So narrowband. In the sense that their complex envelope does not change significantly during their propagation time across. I think I will continue here. Across the array. And we will call this propagation time across the array as tau. And of course, as for previous points, we can indicate here the main idea that these wavefronts are narrowband. Wavefronts narrowband, signals with distinct direction of arrivals in the same carrier frequency, and all our system is linear transmission medium. Based on these assumptions, we can continue with our data model. And first one, we will introduce phasor or analytical signal of the Aasp wavefront. Phasor or analytical signal of the Aasp wavefront. Of the Aasp wavefront. Phasor is denoted as scalar S subscript I, and here we have superscript sign plus for time t. I think in this case, we use this plus sign in the superscript to show that it is analytical signal. And this phasor is equal to alpha subscript I of t times e to the power of j. And here we need to show, first one, it is our carrier frequency, so 2 pi fc times t plus the phase shift. We will use beta I of t. So it is general phasor for the ith wavefront, and we can go. We can show that our I goes from 1 to up to d sources. I will put this equation into the box. Then we can write down transmitted, received, real valued, bandpass signal. Transmitted, yes, transmitted, received, real valued, bandpass signal, which can be denoted as the real operation of the phasor. So we take the real part of the S subscript I subscript plus with this time depending here. Based on narrowband assumption, first we can show narrow band assumption. So we wrote it before that we have this narrowband assumption. In this case, we will have that if we assume the changing of the amplitude of our phasor with alpha I of t, so alpha I of t minus our propagation time across the array tau, it will be approximately equal to alpha I t, because we have narrowband assumption, which means this complex envelope does not change. And also the same thing we have for the phase shifting. beta I. So same t minus tau. And based on narrow beta assumption, it will be approximately equal to beta I t. So then we can assume phasor for time t minus tau. Our phasor S, Si of t with this plus sign. Sorry, of course, not t, t minus tau. Will be approximately equal, let's use, because before we write that here we have approximately equal alpha I of t times e to the power of j 2 pi fc t plus beta I t, like this one. Yes. Let's maybe write down like this one. Okay, so it is my mistake, but here t with this prime sign, this t minus tau. Then we can move the part with this minus tau, and we will have the same phasor. So let me show you. So this part will be equal to e to the power of minus j 2 pi times carrier frequency times tau. So here, tau. And this e multiplied by s of I of t with plus sign. So in this case, we can say that this tau, it is our time delay over received wavefront. And if we assume this delay, we will have only additional multiplication to this e to the power of minus j times 2 pi fc tau. So time delay of the received wavefront in this case, it will be changed by phase shift. without any changes in initial, let's say, magnitude value and initial phase shift value, this beta I. So we have only additional phase shift based on tau. And the same thing we can write down here. The same changing between time delay to phase shift we will have in complex low pass domain. So it also holds in the complex low pass domain. Complex low pass domain. And I think the last assumption for all these data model is that our signals located far from our sensors, and we can say that we will have far field assumption. Far field assumption. Far field assumption. For this one, we have slide number 4. And as before, we can use blue underline for the main idea that it is far field assumption. What we will have with this assumption? The D point sources. So D point sources are located far from the array. Such that their direction of arrivals are equal at each sensor. And here we can write down, for example, the wavefronts are planar. The wavefronts are planar. So this d point sources is not equal to near field sources. So let me show slide number 4, and then we will continue. Here, for example, we have two signals, signal 1 and signal 2. So it means we have d point sources equal to 2. And you can see they have these planar wavefronts here and here. And for example, we have here different types of receivers. So this one is a tropic one, and these receiver 2 and 3 have some beamforming. Oh, sorry. Let's write down complex measurements at the cave sensor at time t. So complex measurements at the cave sensor at time t. And here we will use complex domain with complex low-pass domain description. Complex low-pass domain description. This complex measurement denoted as x subscript k of t is equal to the sum. Here inside we have a subscript k of theta I phi I multiplied with si s subscript I, and here we have t minus tau subscript k, which depends on theta I and phi I. Theta I, phi I. And this sum goes from goes for I from 1 up to D sources. Or we can represent this S of I in a different way. So let's write down the same sum for I from 1 up to D. Here we have A subscript K, theta I, phi I times S of I, Si of t, so Si of t times E to the power of minus j 2 pi times carrier frequency Fc, and this tau of k, which depends on theta I and phi I. Tau k, theta I, phi I. And k goes from 1, 2, up to m. So the number of sensors in our sensor array. So here, this tau of k, and in the first line, the same tau of k. And from first, let's put this equation into a box, and then I will continue. Based on this equation, you can see that we have only the delay part is tau of k. But if we assume the real case, we will have also some path losses. So let's write here path loss is not taken into account. It's not taken into account. If we want also have these path losses, we need to scale Si of t. So it will scale Si of t. So what we have inside of this equation, tau of k and a of k. No. Tau subscript k and a subscript k, because they are both dependent on theta I and phi I. So it will be correct notation. So tau subscript k, which depends on theta I and phi I. It is propagation time. between a reference point reference point and the cave sensor. For the Aasp wavefront. For the I think I will continue here. Aasp wavefront. And here we will introduce the reference point. I think only in the next lecture. So reference point means, let me maybe say you right now. So for example, we have number of sensors in our sensor array equal to 9. And let's, for example, choose the sensor array in the middle as the reference point. So it will be a reference point at sensor 5, and 4 sensors from the left and 4 sensors from the right will be not the reference, but the rest of the sensors. So you will see what does it mean when we have this reference point. It is just how we compute the difference in time between these sensors, or difference in phase when we receive our signal. So you will see it next. And a subscript k of theta I and phi I, it is corresponding complex response. Corresponding complex response of the cave antenna. Of the cave antenna. Or of the cave sensor, of course, we can say. In general, we can write down what we'll have for this tau subscript k in general. And I think I need to show you slides one more time. So here slides 4 up to, let me check. So I will show you first, and I will say you the last slide for this reference. So here the same slide 4. Here we have number of sensors 3, number of sources 2. You can see that we have this far field assumption here. Here you can see the example of an anechoic chamber. Here we have one not the reference antenna, but let's say non-transmit antenna, and usually we test some receive antennas inside of this anechoic channel. And I think we have something like this in KE, maybe in 8th building, or in some factory, maybe. And here you can see just as, for example, the positions of the receive antennas or the receive sensors. And of course, if we go deeper, we need to have the distance between these sensors equal to lambda half, and where lambda is our wavelength of the source. And one more thing, what does it mean with theta and phi? Theta here, it is azimuth. So if we look to this one, here we have x, and here we have y-axis, like this one, x and y. And azimuth goes on this plane of x and y. And phi, it is the elevation. So it is the angle between x and y and axis z. So this one. But of course, I will one more time show you in notations these things. And we will go to these slides one more time. Then I will give you general equation for propagation time. So let's start with this general thing. So here, 7. Slide number 7. In general, for propagation time, we can write the following equation. Tau subscript k of theta I phi I equal to 1 over c times vector p subscript k transpose times vector d which depends on theta I and phi I. I will put this equation into a box, and also I will highlight tau of k, tau subscript k of theta I phi I with yellow color. So this part here. So in general, we have this equation where c is wave propagation speed. Wave propagation speed. So we usually assume it as 3.3 times 10 in the power of 8 meter per second. Then this vector p subscript k. So p k. It is coordinates of the cave sensor or antenna. Of the cave sensor / antenna. And this PK is on the real plane of size 3. Because we need to have 3 values to set the coordinates for the sensor. So this PK is equal to, we can write down P subscript X of K, P subscript Y of K, and P subscript Z of K. And then this theta and phi theta is located between minus pi and pi. So minus pi and pi. And from the left side, it is greater than minus pi, but from the right side, we can have this equation to pi. It is our azimuth. Azimuth. And phi has values between minus pi over 2 and pi over 2, and it is elevation angle. And the last thing here, the vector z. And I think we will end with this one. So d is equal to another thing, minus omega, and d means unit vector pointing in the direction of the source. Okay, I will continue here. Of the source. And the omega vector will have the same unit vector pointing in the direction, unit vector pointing in the direction so let's see. So if d is equal to minus omega and it is of the source, so omega it is the direction of the propagation. So we receive the signal from this this side, which shows us omega. So in the direction of the propagation. So for example, the source is located in the front of me, but the direction of the propagation will go to my back because it sends data like this one. So I point it, let's say, in the forward way, but the propagation of the signal is in my back. So this pointing back. And for this omega here, we have, I think, slide number 8 or slide number, let me check, slide number, slide number 7. So the same slide number 7. And here on this slide, we can see what we'll have for this omega here. So you can see omega is equal to minus, and here we have it is the column vector. First value it is cosine of phi times cosine of theta, then cosine of phi times sine of theta, and last value it is sine of phi. I think we can end here for today. Then we will continue in the first day. So the same, we need to finish this data model. We will have a measurement vector next, and we will use well-known for you eigenvalue decomposition, and we will use it to estimate subspaces. And you will see for which purposes. And of course, then we will start the main methods to estimate the signal parameters. So that's all for today. That one was really tough, but we needed to end this RLS algorithm. Wow.